All right, today we're tackling something huge. It's one of the most fundamental ideas in all of science, the very thing that holds our entire world together. But here's the twist. It's also surprisingly tricky, even a little mysterious. So, let's just dive right in and try to unravel it.
I mean, think about it for a second. What holds the world together? It sounds like a simple question, doesn't it? Everything around you, everything. The screen you're looking at, the air you're breathing, you're made of atoms. So why aren't we all just disintegrating into a cloud of cosmic dust? What's the invisible glue holding it all together?
Well, the short answer is the chemical bond. But that's where things get complicated, because behind those two simple words, there's more than 100 years of intense scientific debate, of revolution, of mind-bending discovery. You see, figuring out what a chemical bond actually is, well, that's been one of the biggest challenges in all of modern chemistry.
So to really get a grip on what we think a bond is today, we've got to go back, way back. Let's look at the very first stabs people took at explaining this invisible force.
In the beginning, the ideas were, pretty physical. Back in the 17th century, they literally pictured atoms with tiny little hooks on them, just latching onto each other. Then Newton comes along and everyone's thinking shifts to these mysterious forces, kind of like gravity, pulling atoms together from a distance. It wasn't until the 19th century that chemists started getting, more chemical about it. They came up with ideas like affinity, this sense that some atoms just like each other, and valence, which was basically a number telling you how many hands an atom had to hold on to others.
And this is where those early ideas really hit a wall. See, a compound isn't just a mix of ingredients. Think about it like this. If you just mix hydrogen and oxygen gas together, you just have a mixture of hydrogen and oxygen. But if you let them react and form chemical bonds, boom, you get water. Something completely new with totally different properties. A tiny hook or some vague force? No way that could explain such a radical transformation.
Nope. To explain that, scientists had to basically tear up the old rulebook. They had to start from scratch. And it wasn't just a chemistry problem. It was going to take a full-blown revolution in physics. And you know what? That revolution has a date, 1927. That's the year two physicists, Heitler and London, took the brand new, super weird rules of quantum mechanics and pointed them at the simplest molecule you can get, hydrogen. What they found? Well, it changed chemistry forever.
Okay, so this is the absolute key. Quantum mechanics showed that when a bond forms, something incredible happens. The electrons, they don't belong to their original atoms anymore. They become part of this bigger collective system, the molecule itself. It's this sharing, this idea of community property, that creates something brand new. It's not just two atoms holding hands, it's a completely new entity.
So, problem solved, right? Well, not quite. Even with this massive breakthrough, the story was far from over, because now there is a new problem. Okay, we know it's quantum, but how do we actually describe it? How do we talk about it? This question kicked off a huge intellectual battle that pretty much defined chemistry for the next half-century.
What happened was, two competing languages, you could call them, were invented to try and explain the quantum bond, and they came at the problem from two totally different angles. So, on one side, you've got valence bond theory. Think of this as the chemist's favorite. It was championed by guys like the great Linus Pauling. It's more intuitive. It pictures a bond as a specific link, right between two atoms, where their little electron clouds overlap. The atoms are still kind of themselves, just in a partnership. But then, on the other side, you have molecular orbital theory. This is the physicist's approach, way more abstract and purely quantum. It says, forget the individual atoms. When they bond, all their electron clouds merge together to form brand new molecular clouds that cover the whole thing. The original atoms have basically dissolved into a new molecular identity.
And for decades, these two camps went at it. But, when it came to the really heavy-duty calculations on big, messy molecules, the molecular orbital theory often came out on top. And here's the thing. It wasn't necessarily because it was more right, but because the math was just easier to work with. Sometimes practicality wins.
So, where does that leave us today? Have we picked a winner? Not really. Our modern picture of the chemical bond isn't about one theory being right and the other being wrong. It's more like a greatest hits album, a rich, complex mix of all these ideas from the past.
Just look at how nuanced our understanding is now. It's like we have this amazing toolkit. We'll pull out a concept from valence bond theory, like hybrid orbitals, when we want to talk about the shape of a simple molecule. It just works. But then, for other things, we grab the big idea from molecular orbital theory, delocalized electrons, to explain how some electrons can roam across an entire structure. That's what's happening in metals, for example. The bottom line is, A bond isn't just one thing. It's a whole collection of concepts we use to describe an incredible range of stuff, from the insane strength of a diamond to the delicate hydrogen bonds holding your DNA together.
So really, the main takeaway here is that the invisible glue isn't just one type of glue. It's a whole spectrum of interactions. It's this incredibly powerful and flexible idea that covers everything from the super tight covalent bond to the much weaker forces that, make water wet.
And that leaves us with one last kind of mind-bending thought. All of these models we've talked about, the little hooks, the overlapping orbitals, all of it, they're just stories. They're human inventions we created to try and get our heads around a deeply strange quantum reality. So if the smartest people on the planet have been arguing for a century about what a bond even is, it really makes you wonder, what does one actually look like? Can our brains ever really picture the invisible glue that's holding absolutely everything together?